Hi, I'm Graham Stevens, application engineer here at KETIV, focused on ANSYS products. I have over 25 years of experience in product development, consulting, and simulation. And I provide application support for ANSYS mechanical, thermal, high frequency, and low frequency electronic applications. And today we are covering Icepak, the thermal side of electronics. This is sort of a brief agenda here. We're just going to do an introduction to Icepak. What is it? There's some different flavors of it. What you can simulate with Icepak, what kinds of outputs you might get. And then I will do a short demonstration of an air-cooled and a water-cooled PCB enclosure. So if we have a PCB enclosure and we want to cool it with, say, some fans or a heatsink, or cool it with a water cooling bed, we can do that. And I'll demonstrate that. And then I'll be focused on a number of slides at the end in terms of, after this brief introduction and flavor of what's possible, I wanted to give you guys a lot of new links to more advanced topics and workflows so that you can kind of pick and choose where you want to go and how you want to go about it in terms of some of the more advanced workflows, and then where to obtain further information and more training. So this will be somewhat basic, just kind of focused on the basics, and then with a lot of links and further information to get you going as you get into Icepak and do more complicated simulations, including coupled simulations with a lot of the other ANSYS suite. So what is Icepak? Icepak is a solver for electronics thermal management applications. It predicts airflows, temperatures, and heat transfer in integrated circuit packages, so at the very small scale, but then also at PCBs, electronic assemblies, and power electronics. It was sort of created initially as we have a box. We've got some heat flow, whether that's water cooled or air cooled or radiation. And for electronic applications, you have a lot of additional widgets. So you might have a heat sink in a box or a fan in a box. And Icepak has automatic creation features for some of these common methods of cooling for electronic applications. And so it's a special purpose built application for this specific cooling off of PCBs and electronic boxes. And then under the hood, Icepak uses Fluent's Green-Gauss finite volume method with a cell-centered formulation, which is a particular CFD method to solve the Navier-Stokes equations for transport of momentum, mass, and energy when calculating laminar flow with heat transfer. And so, typically similar to finite elements, we take the control volume, chop it up into pieces, discretize it, and then start solving Navier-Stokes equations for transport of momentum. And you can sort of see this flow chart in terms of how this gets solved. We have solving the pressure correction continuity equation, then updating mass, flux, pressure, etc., and then finally solving energy additional turbulence equations and seeing if it converges, and if not, we repeat. And so relative to turbulent flow, where you have relatively high Reynolds numbers, you have additional transport equations are solved. So this is listed here. You're starting with the zero equation model, the simplest and quickest, to one equation models, and then two equation models, including enhanced wall treatments. And as we go to these more complicated models, obviously the solve time goes up somewhat relative to doing turbulent flow. So very high amount of capability, all the capabilities of CFD and Fluent, with a few exceptions we'll get to in a few minutes. And so Icepak itself comes in two different flavors. One is called Classic. It's an older interface. It's icon-based. It's accessed through Workbench. and you have these various primitives, and you have to sort of know what these icons are and open them up. But essentially, it allows you to create grills, create PCBs, create enclosures, plates, walls, blocks, fans. There's a bunch of primitive objects here that makes this job of estimating thermal transfer for electronics more easy. And it's accessed through Workbench. And then there's the latest called the ANSYS Electronics Desktop, or AEDT, Icepak flavor. And this is the latest version of Icepak. It has almost all of the features and macros from Icepak Classic have been transferred over and migrated to the new interface. And the advantage here is that you can much more easily interface with the other parts of the ANSYS suite. So if you have an HFSS analysis and you want to couple it with Icepak, you can do that very easily. If you have a Maxwell analysis, you want to couple it with Icepak, you can do that very easily as well. So there are, so we strongly advocate jumping into the AEDT if you are new to Icepak, but I wanted you to be aware that Classic is out there, and you'll sort of see it in some older videos, and it has some useful information as well. So I'll discuss that as we go forward as well. When we're thinking about Icepak and doing thermal analysis, you'd also, within the ANSYS universe, have some other alternatives. So within ANSYS Mechanical, you can use ANSYS Mechanical for thermal analysis as well. And some of the advantages of using ANSYS Mechanical is, of course, it easily couples with Mechanical to calculate mechanical stress. You can do that with Icepak, but it's a little bit more convoluted. And FEM uses more memory than FVM. But essentially, you have this steady state approximation. You can do these heat transfer modes, but convection, you do it as using a heat transfer coefficient. But if that's an approximation that you don't want to make and you want more accuracy, you should definitely jump into Icepak. And then, of course, there's Fluent that we talked about earlier. It has more CFD knobs, models, and methods. So Icepak has been somewhat simplified for this electronic packaging application. And Fluent can handle two-phase flow, or Icepak can't. So if you need to do two-phase flow, you want to jump to Fluent. And then, of course, the setup for electronic simulations can be slightly more complicated in Fluent. So instead of building an automatic heat sink, which we'll see in the demonstration later, you have to create that heat sink in geometry and then bring it into Fluent, and changing, say, the number of fins and doing a parametric analysis is slightly more complicated. You have to, again, sort of go back through space claim to do that sort of geometry manipulation. Whereas in Icepak, it's a simple parameterized object that allows you to do those sorts of explorations a little bit more easily. So just wanted you to be aware of these alternatives in case they're applicable. And then here are some examples of what you can do with Icepak. So we have these different kinds of thermal simulations, from a heat sink fan assembly, doing a thermal conductivity map of a PCB, animation of temperature contours and fluid streams for a graphics card. We might have a projector bulb cooling application for a projector. We might actually want to look at the temperature map of an LED bulb and go a little bit smaller. We can look at velocity vectors around a drone model. And finally, we can animate particles and traces through a data center. So FVM is a finite volume model. One of our questions earlier. So when we think about modeling fidelity, typically you want to start with a very basic model within Icepak, where you have just block primitives. We have the PCB board just cast as a block. We might have a chip or a couple of heat sources on the top of the surface of that PCB board, modeled as a block, but as smaller blocks themselves, and then a simpler heat sink and two-dimensional fans, and a grill. And this sort of primitive setup is usually enough to get you what you need in terms of heat transfer. But obviously the model fidelity is a little bit lower, but this will definitely kind of allow you to play with different options. Do I need water cooling? Do I need this or that type of fan and this or that type of heat sink? So we can start optimizing and getting a rough picture of where we are using these simple primitives and much faster analyses, which is of course the advantage. But then if you want to, you can add in a more detailed heat sink. You can take a PCB board and pull it into Icepak with traces. You do three-dimensional fans. And then of course, you can also add in MCAD, the specific design of your object with high fidelity, which obviously takes a lot longer, but we can get very detailed and very precise as well. So just keep in mind that we kind of want to start with keep it simple, stupid. We want to start with this primitive, make sure that your heat transfer conditions are appropriate and working, and then add in the complexity of the design as you go forward. Okay, so now I'm going to switch over to the demo. All right. Sorry. Oops. Switch this here. Larger screen. Okay. So I have a brief demo here of just an Icepak scenario where we have a PCB board that is in block format. With a couple of standoffs, and somewhat hard to see here, but I have just a single chip and then a little bit of thermal paste, and then on top of that a heat sink, and then finally a fan blowing air across the heat sink. And I created a kind of conducting plate here just around the edges and the outside, so that we actually, all this air is an enclosure, but we're just modeling just this enclosure with a grill here on this face right here. And so to model this, you start with sort of Icepak primitives. And so these are these icons up here in terms of geometry creation. So we draw a box and have face here and go to the size here. And then for the properties of this box, we have the properties here, and you can now adjust the position or the size of the box however you like in terms of getting it to be the right size. If for some reason we just added this in and it turns out it's a little bit too high, we can also take this box and edit and move it. So now we can take it and move it to wherever we like within the design to, again, sort of place it and get it set appropriately. We can also, when it comes to these primitives and moving them around, we can use a coordinate system. So we have a global coordinate system here, and if I create a relative coordinate system, so the global coordinate system is right here, and so relative to that, I'm going to pick on this point, and now I have a coordinate system here that says relative CS. And if I go back to this box and its properties, the create box, we have a coordinate system here. And if I change it to the relative to coordinate system there, and I've got to get rid of the move operation. Sorry. Here, let's just suppress the move. Is this the right? Yeah. Okay. So this was originally created in the fan coordinate system, but if I take this position 0, 0, 0, now it's no longer relative to this coordinate system out there. It's locked into this box coordinate system here that I just created. And so by now changing this relative coordinate system, which is at 50, 170, 170, I can do, say, 20, 150, oops, and 10, say, and change its position. And then, of course, the box follows it as well. So this is a very good way of positioning and moving different objects around, is to create their own, to have their own coordinate systems. And in particular for fan objects and heat sinks, it's helpful to do this as well. So this is kind of basic geometry creation. And then say I want to create a fan, I would go to 3D components here, create, and there's a fan or a heat sink or a PCB object. And these are some of the objects I wanted to go over with you. So for the fan, if we do, I'm just going to edit its definition. So when you create the fan, you'll come to this window here, drop-down box, where you create the name and the company, the model number of the fan, and then describe it, whether it's 2D or 3D. So earlier we talked about the more primitive objects. You can do just a two-dimensional fan, which has a face and blows air, but doesn't have a third dimension, or a 3D fan, as I have here. We can change its shape from rectangular to circular, which cross-section it's at. And this is just defining the fan characteristics. So how big is it in terms of its total radius, its hub radius, and then the casing around it, and which direction that fan might be in. So we can see we've got the plus Y and the minus Y here. We can change the height, etc. And then if we press next, now we're talking about the fan characteristics in terms of its direction, which way it's blowing air. Is it fixed volume? Are you using a fan curve or fixed mass flow? Do you have swirl RPM? And then what materials it is. You can sort of use the defaults or pick a known fan and adapt these parameters to it. And then we have an area here for parameters and finish. And then this fan is then created and placed into the design. Similarly, for heat sinks, you can do a heat sink here with the name, company, and model number, and then the different characteristics of the heat sink. So where does it start? Which plane? How high is it? What is the base length and width and height? And then how big are the fins and how thick they are and what the fin count is. Once we've created the geometry, we have different thermal input and output conditions where we tell Icepak what's happening thermally. And so in this particular case, I created a small box that's underneath here that is the silicon chip. And you would pick on the silicon chip and then right click and assign thermal. And in this case, I did a block source. And when we look at the properties of this, we can define what the total power of that block is and what that's looking like in terms of how much heat's coming out of that box. Similarly, for this air box, I picked on a number of faces for the air box here and here and here. Well, not the ends, sorry. Here and here, and then around to the bottom, etc. Grabbed all those faces and then assigned thermal conducting plate here. And that then has a specification relative to thickness and the type of material. So it creates a thin a thermal plate model here. And this is somewhat of an approximation, of course. So if you want to get more accurate, you would actually model this in solid, where you create a box around this that has a thickness. But for my sort of initial model, I just wanted to do something quick and easy. And then finally, I have here with a thermal grill that I added as well, which again, you have properties of just loss coefficient and what sort of resistance type it is and free area ratio, et cetera. So with these defined, we then start thinking about meshing and monitors. So in particular, I wanted to look at the silicon box here, and I wanted to show only, and then grab this face, the top face here, and assign a monitor to it. And then I grab the bottom face as well and assign a monitor to that. So now I'm looking at the top and bottom of that silicon block. And the advantage of that is, as it's calculating, we can take a look at those temperatures and see if they're as expected. And when we define this monitor, we can define it as looking at mass flow, volume flow, temperature, or heat flow rate. So in terms of what we're monitoring. So it's useful as well to look at if you've got a face where mass is passing through it. You can examine that as well during the run. And then finally, we start looking at meshing. So in this particular instance, I'm editing the global region here and just using the standard mesh resolution, which is a good place to get started. Obviously, we can take it finer if we need to. And then there's a bunch of advanced meshing if you want to jump into more advanced meshing, where there's an additional course for that. But I generally just sort of start with the standard and go with that. But in this particular case, we have this heat sink, and we know the heat sink is that we want a much finer mesh around this body. And so for this particular case, we want to create a mesh region around it to say, I want to mesh more finely in this particular area. So to create that mesh region, one simple way to do it is to just start creating a box that basically envelopes this area. And so now I have this box created. If I take it off of model so that it's a non-model box, and then right click on it and do a mesh region, which is what I did earlier for box 6. So I'm going to delete this and just jump to the mesh region. We can now change the properties for this mesh region. We say, okay, for the heatsink, I want to go to a fine resolution. Or for the heatsink, I may want to specify more advanced settings for the mesh. So this is another way to sort of say, well, refine the mesh a little bit more finely in that area. And then other mesh operations that are useful is we need to generate the mesh here, and we can also view the mesh with the mesh viewer, and then assess its quality as well. So once meshing is complete, and there are courses I'll be referring to take you through some of those more detailed meshing considerations. We do an analysis setup where we add a solution setup, and then do properties here. Typically, you would use some of these typical defaults for forced convection, natural convection, mixed convection, or conduction only. Is a great place to start. In this particular instance, we're doing forced convection. We might want to include gravity. And so all of these settings are basically here for you. But if you want to get into some of the more advanced options, you have the ability to do advanced options. And if you know CFD, you've got various discretization schemes that you can use if the standard defaults are not working. And so this is how you get access to those advanced settings. And with that, you would click on, right-click on the setup here and analyze, and then you would start looking at your temperatures. So I ran the model previously, so this is the temperature results that I'm getting. So we're getting this, coming up to a 92 degree chip with this particular level of fan cooling. And I have this monitor that's requires you to be in this more orientation to get the legend to be appropriate. But so this is what we can do in terms of temperature plots. We can also do a velocity plot where we look at the velocity of the airflow through the box here. And so we can see we're getting more airflow here at the top of the vent because as the heat comes off, we get more airflow there. So this is, allows you to sort of visualize what's happening from either a conduction perspective and the temperature through the bodies or in the air as well. So that is what I wanted to show in terms of the air-cooled kind of simple model. And then we can also perhaps we now want to make it a little bit more complicated or a little bit more fidelity. And we want to, instead of assuming that the PCB board is just a simple block, we might want to actually grab some electronic data in terms of the actual layers and model that board with the actual copper traces that are being used for the board. So for this type of analysis, and again, I kind of did everything basically the same, except I'm substituting in what's known as this 3D component and a PCB body. And for this PCB body, essentially what we do is we would import an ODB++ file or an IPC 2581 file from ECAD from where the board is created and designed. Import that into HFSS 3D layout, which I've done here. And this gives you a model of a very detailed model of the board and all of its traces, including all the layers on the board, which of course, it's very important to make sure that these layers, both the thicknesses and the materials, are correct, because this is what Icepak goes off of when it comes to putting together the conductivity for this board. But once you've double checked that and have this PCB board in AEDT, we then simply back in Icepak create a PCB object here. And I'm just going to go to the properties here. And again, we have sort of name, company, model number for the board. And to set this up, we do this setup link where we use this project, grab the PCB design that we already imported, have these couple of checkboxes, check the variables, board settings here in terms of the outline of the board, and then finally part settings if that's necessary. And then once this is created, if you have power dissipation on the board, you can add it here. If you want, then this is a power dissipation across the entire board. So you can specify a wattage that way, or you can specify thermal sources. But then you also have a resolution here for the metal fraction. So basically what Icepak does is it takes this PCB board, chops it up into smaller pieces, and then calculates the conductivity of each piece, whether it's sort of mixed conductivity if we have copper and FR4 together, what's the conductivity of each of those individual pieces relative to this larger piece. But we have a resolution associated with that approximation essentially. And that's what this resolution is here in terms of how fine are we chopping up the board relative to calculating that metal fraction and conductivity for the board. So this setting is important as we go through. And then that PCB board is now set in the model, and we can run it and get somewhat similar results relative to what we just did earlier. And I'll just sort of show the temperature result, where in this particular case, I created a 2D object here as the source for our 2 watts of power, and then Icepak calculated the conductivity through the board and all of its layers, in addition to the fan cooling, to give us our final temperature profile for the board here. And similarly, we can look at the velocity of the airflow through the box. So that's kind of an example of pulling in a PCB board into Icepak. We can also do water-cooled designs, where we again have our sort of simple shapes here. And in this case, I created a water channel as well. And we'll probably do a separate webinar on an easy way to create some of these shapes. But essentially, we create a circle and create a path, and then use this. There's an option here to sweep along path to create this internal water channel. And we name the material for water, and then have a water inlet and outlet as some of our thermal conditions. So this is an inlet where we specify the temperature of the water coming in, whether it's mass flow or velocity, and how much mass, in what direction. Same thing for the outlet. In this case, I created a free air box here. So we just have the design is open to the air, but we have to sort of stop somewhere. So you want to have a large enough air box where your velocity is pretty small, and you've basically gotten to ambient velocity. If it's too small, it will impact the results. And then finally, as I mentioned, I created a sheet object, in this case, just a rectangle to represent the heat from the chip, and followed all the same steps in terms of doing the analysis. And we similarly get sort of a temperature, simple temperature profile here of now we have a water-cooled body that's cooling everything to 10 degrees, except for right where the chip is. And then you have some conductivity that gives us this profile of what's going on with the chip. And in this case, I created a box for FR4 in terms of representing the PCB board. But you could do the same prior analysis we just did with the PCB object if desired. So that's just a brief overview of Icepak and its capabilities and how you run through an analysis. One thing I didn't touch on is material properties. So if we have a box and we're an object, we assign material and come to a materials library, and then you have a system library of typical materials. We also have different materials. There's something called Granta Materials Database for simulation, which is a repository of thousands of materials that are all basically done for you. So if that's of interest beyond the sort of standard, more simple set or system material library, please feel free to explore that. And then, of course, for any of these materials, I might have FR4, but I might have my own material that I want to do. And I can clone this, call it a copy, and now I can start modifying these properties. And if I want to, change the relative permeability to, 50 or whatever it is my material is, I can change these materials, press OK, and use this material, which is now in the database or in this particular project. And if I want to use that same material with other projects, I can export it to library and export it to a personal library. So in any case, you can modify materials to get to the exact properties of what you're looking for, and make sure you've got thermal conductivity parameters, obviously very important relative to conduction. With that, I think we are finished the demo. Let me get back to the slides here. So that was just sort of an overview of generally how Icepak works and how to set up an analysis within Icepak. But in terms of sort of walking you through each of those steps in a little bit more detail, especially the meshing and so forth, we highly recommend starting with ANSYS's Learning Hub. And within the ANSYS Learning Hub, there's a thermal management learning room, which I've given you a link here. So there's a kind of precursor for thermal management basics in terms of basics of thermal management or thermal heat transfer. And then these two courses, Introduction to Icepak AEDT and Advanced Icepak AEDT. I highly recommend you kind of start with both of those courses to get used to running the Icepak analysis tool. And then you can combine it with HFSS and Maxwell, and these self-paced learning courses that walk you through combining that. So we might have HFSS and get a thermal profile from HFSS in terms of dielectric losses that might be happening there, or resistance losses from Maxwell that we want to pass to Icepak as a thermal heat source, and vice versa. You may want to, if your thermal results then impact your material properties, you may want to do coupled analysis and pass the information back to Maxwell and back and forth. So that's a coupled analysis. So this is sort of the starting point for doing those more complicated two-package types of analyses. And then within the ANSYS Learning Hub, there's a number of advanced topics and advanced courses. There's a PCB workflow in ANSYS Fluent, if you're interested in how to do this with Fluent, a cold plate workflow in a little bit more detail than I did earlier, some best practices on convergence, and then a bunch of different webinars on Icepak meshing, multiphysics optimization of electronic systems. So I mentioned how we might have a heat sink total number of fins, and we might optimize that or optimize the size and shape of things. This is a good place to start relative to optimization. The ECAD import for PCBs and packages. This video is a great place to start with that in terms of formats and making sure the ins and outs of that. And then finally, thermal network modeling is there as well. And so I mentioned that we have all these different packages that interface with Icepak. And this is sort of an example of what's possible. So I just wanted to acquaint you with the possibilities so that you investigate further as necessary. And so I mentioned within AEDT, we have ANSYS HFSS, Maxwell, and Q3D. And those can provide electromagnetic analyses to get you a heat distributor or a heat source and feed that into Icepak, which then does the thermal analysis and back and forth. If you're interested in actually looking at the electromagnetics of the board itself in terms of joule heating and traces, SI Wave can provide a thermal distribution of the board in terms of what's going on from a current perspective and where heat is there, and you can transfer that back and forth to Icepak for more detailed analysis. At the chip level, ANSYS Red Hawk allows you to go back and forth to Icepak as well. And then finally, we have a couple of analyses at the bottom here, ANSYS Structural and ANSYS Mechanical. If we're looking at how does the heat impact the mechanical structure of a device, you can go use Icepak to pass information to mechanical. Similarly, on the reliability side, ANSYS Sherlock analyzes the reliability of PCB packages, PCB boards and components, and Icepak can be used to improve the accuracy of Sherlock's calculations as well. And then finally, ANSYS Twin Builder. If we start thinking about the system level, you can do a reduced order model of an Icepak analysis and pass that to the system level using ANSYS Twin Builder. And that allows you to do more system level analysis. And the only other thing I want to mention on this slide is there's an EM to Icepak ACT, which is can simplify this electromagnetics setup essentially. So be aware of that. But of course, the ACT system may be changing in the next few years, so that may change over time. But I just want you to be aware of that for now. And then I just wanted you to be aware of a few other resources that are out there. So there's on YouTube, and many of these are older videos, so they reference Icepak Classic, but a lot of the techniques, of course, are used essentially, or the underlying theory is still the same for AEDT. So many of these videos are very useful. There's a migrating from Icepak Classic to AEDT tips and tricks. This how metal fractions are used to calculate thermal conductivity in an ECAD in ANSYS Icepak is an excellent video relative to showing you more details on that resolution that we covered and what should you pick there. Have I got a high enough resolution or not? That's answered in this video. And then a number of other possible topics that might be of interest, including at the bottom here, importing Allegro APD SIP format ECAD into Icepak via ODBB++ or IPC 2581, debugging divergence, and then a Sherlock to ANSYS Icepak for temperature cycling video as well. And then ANSYS, in addition to YouTube, ANSYS has also created an innovation space, which has mini courses and larger courses that cover a lot of Icepak related topics. So we have ETM using ANSYS Maxwell and Icepak, ETM using ANSYS HFSS and Icepak, and then a number of Fluent or Fluid CFD related videos that kind of describe the theory and what's going on and some of the models. And so this is a place to start in terms of some of these potential topics in terms of CFD, points of interest that Icepak uses the same methodology. So all of these are applicable to your Icepak work, and it might be useful here in terms of some best practices and forced convection and turbulence modeling. And then I kind of rattled off all these different sources. They do change over time. So in ANSYS's Resource Center, they're continually producing webinars. This is an interesting one that's Icepak related, where you might have an Icepak simulation workflow that you'd like to automate. And so there's something called Pi AEDT that allows you to automate your thermal simulation setup and get more have that setup process be quicker and easier. So we'd recommend that. But do take a look at this link periodically in terms of additional webinars that ANSYS produces. And then finally, for additional support, including model setup, double checking what you're doing, any help you need in terms of finding your way through the ANSYS Learning Hub. If you have issues as you're modeling, please do email support@ketiv.com so that we can help you. If I can't help you, there are another 50 or 100 Icepak-focused engineers at ANSYS that can, and so we'll get you the help you need so that you can get over those humps. And then finally, I'll just mention that KETIV offers simulation services as well in the mechanical, fluid, and electronics realm. So if you have some additional work, we do training where you do it 100% versus this more simulation services where we do 100% and sort of anything in between. So please do take advantage of simulation services if you're unfamiliar with a particular analysis, if you're running into capacity issues, if we can be of service and help, we'd love to do that. And with that, I think we're done.